My name is Ruizhe. Today I have the honor to host Roger. Roger is an ideal guest to help us look forward our Ethereum centralized comfort zone. At ETH, he has been a long respect professor leading authorities on distributed system, and now his, I would say, main job is helping Anza to build the next layer of consensus protocol, and that commitment is Alpenglow he's going to talk about. And beyond those details, which he'll talk about, I think it's really important to recognize why this matters. Um, Solana is no longer like 2023 has tens of outrage. It has a very mature network, has extremely loyal community, and it's important for us to understand this new ecosystem. And as researchers, we are often focused on Ethereum. We have a lot to learn from this new role, and Roger will be the person who guide the way. And the floor is yours.
Thanks so much, Ruizhe. So that was a nice introduction. Uh, Let me share my screen. So I hope you can see it. Yeah, so I would like to present this Alpenglow consensus protocol in this talk. Like the first part of the talk will be about that, and the second part is actually more about economic incentives and how to get these right, I would say. So before I start, I quickly want to move to, oops, to just a bit of philosophy. So for philosophy, I often like to show this little quote from the 1940s. People at my age made a lot of fun when they heard about this quote later when computers actually became popular. But back then, Thomas Watson, which was the boss of IBM, said that I think there's a worldwide market for maybe 5 computers. But nowadays, we can probably fix that quote by just moving the worldwide down to the 5. So we have a potential market for maybe 5 worldwide computers. And what I mean by worldwide computers is, this blockchain thing. So this basically centralized machine which lives in the whole world and, does things for you. And what I want to see from such a computer is basically performance, the support for, arbitrary computation for smart contracts, and it should be decentralized. And if you look at many of the top blockchains or many of the top decentralized computers these days, they don't have all 3 of those things. And we kind of hope that Solana can be one of those 5 machines which have all 3 of those things. In particular, we care about decentralization, meaning that there's not a single company basically operating the whole thing. So that would be making things much simpler and much easier to manage. And why this is important, we have seen, for instance, you have maybe heard of this GameStop incident a few years back when some basically markets immediately decided that these GameStop stocks should not be traded anymore because some of their friends had problems with it. So, if some single entity controls the whole system, that could always be a problem, right? As soon as their friend needs help, they might want to do something fishy. So that's basically a bit of philosophy. Let's go right back to where I started. So the Alpenglow consensus protocol. So we have pitched this new consensus protocol, and actually just recently the validators of Solana, the people basically hold the currency and have voting power, they voted on this. And they decided with basically 99% of the votes to accept this new consensus protocol. So at this point, it's not just a paper anymore, but it's actually going to be a reality. When I say we, that's not just myself, it's also Kobe and Quentin, 2 of actually my former PhD students who also are part of this protocol design. And we're all from ETH Zurich, as we just heard. And maybe I should say this in this crypto world. So this is not Ethereum, okay? So this is actually a university. Sometimes it's highly ranked even. Sometimes even #1 in computer science in the world. So, it's a respectable place, I guess. So at Solana, we try to have a very performant system. So our motto in some sense is increase bandwidth, reduce latency. We want to have many transactions per second for increased bandwidth, and we want to have fast finality. And when we look at bandwidth, actually, Solana is already very good. Okay, so Solana has a so-called turbine protocol, which is very fast in disseminating data, and conventional protocols will be much, much slower. Usually conventional protocols have some sort of bottleneck. There's, a leader which has to talk to, lots of other nodes and send slow messages because of that. Or there might be some other type, or you have heard maybe of these DAG protocols. They're also already much better, but they're not yet there where Solana is actually. And with Alpenglow, we cannot improve that really much, but maybe a little bit. So we can maybe optimize this a little bit, and I explain how later. So that's for the increased bandwidth. The reduced latency part is maybe even more interesting. So Solana finality currently, it takes kind of like, people say maybe 12, 13 seconds until when you send the transaction to the system until it's final. Solana has also something called optimistic confirmation. This means that you send a transaction to the system and you can be almost sure that it's final. Okay, so it can still be reverted in theory, but in practice it rarely happens. That's in the order of 500 to 600 milliseconds maybe. This is, not quite a fair comparison because one is really final. So we know that at that point the transaction cannot be reverted anymore, and the other is more like a signal. So it's a bit of an apples to oranges comparison. With Alpenglow, we can actually bring this finality much lower. We can bring it down to maybe 150 milliseconds, and even this is somewhat conservatively estimated, I would say. So you can maybe bring it down even further, and this would allow for quite a few new applications. So this is really the apples to apples comparison here. And if you look at the competition, this is a bit sloppy slide, but basically I would say they're, the fastest of them are maybe in the range of 400 milliseconds finality. Of course, there's also something like Bitcoin, which has a much, much slower finality, or Ethereum for that matter as well. This is an apples to apples comparison, but depending on how the network looks like, it could be slightly different apples. But no matter what, we believe that we really have a winner here with Alpenglow. We have a very fast consensus protocol. What else is important? Security is important. So we want a highly secure system which cannot be attacked easily. This is something we care about, and we have some novelty here as well. What we have is what we call 20 plus 20 security. And what we mean by this is that we have 20% of the stake can be Byzantine. So this is in the order of maybe 20 billion US dollars. So if you put more money into attacking the system than 20 billion US dollars, then you maybe can attack it. But on top of that, we have also 20% crash failure. So many nodes in distributed systems sometimes halt and they don't do their job for some time or a bit slow or something like that. And that will be covered by this. So altogether, we have up to 40% of the nodes, which can be, either slow or crashing. And just 60% of the nodes basically carry the whole protocol. This is not necessarily better than the competition. The best competition basically has usually 33% security, but that will be fully Byzantine security and not, this 20 plus 20, which is higher, but then also just has, part of it can just be crash failures. Okay. And finally, we try to keep it simple, kind of like this picture here, where you have, this original protocol of Solana, which is very, very complicated. Barely anybody understands it. And I even would say, even at this stage, I barely understand it, even though I've studied it for months now. And we have Alpenglow, which should be not only faster and better, but also simpler. Okay, let's stay with the memes. Maybe you have seen this before. So this is this Argentinian president, and he has this whiteboard. On the whiteboard, he has little stickers, and the stickers are the ministries in North Argentina, and he thinks he should get rid of them. And that was sort of like our ambition at the beginning when we joined Anza, which is the engineering company of Solana. We wanted to, have this moment as well. We wanted to understand what can we get rid of, which protocol parts do we still need. So this is essentially the Solana whiteboard as it is right now. Maybe I've heard of proof of history, maybe the other terms you don't know so well, but proof of history is something that is sort of known for Solana. And actually, you know, we really get rid of many of these stickers. Basically, all of these things are gone. The turbine protocol we like, but we still replace it with something which is slightly more efficient, as I said before. So we want to have a bit more transactions per second. So this is the rotor protocol. And then we need a voting part. And for this, we have been inspired by just recent research. So we looked very much into what have the consensus people come up with in the last few years. And we were especially interested in the simplex line of work, if you have heard of this, or Banyan. It's actually work from my group as well, which have some advantages. And basically what we're presenting here, we call it the voter protocol, and it's kind of the combination of these two ideas. So we have rotor, which is the data dissemination, and we have voter, which is the actual consensus protocol, and those two together make up Alpenglow. So I'm going to just explain this in the next few minutes, rotor and voter. I hope if you have general questions, you could already ask now, I guess. I don't know if there's anything coming in, but if not, then I just, present these two protocols.
Yeah, there is a small question on the competitions. And I think the question is really, what do you think will have the same level of speed and bandwidth and security and you take as competitors nowadays?
Yeah, that's a nice question for me to answer, I guess. So right now, I would say there are protocols which have similar speed, right? But something like, for instance, Hyperliquid comes to mind, which has a similar speed. But these protocols are not decentralized, I would argue, right? So usually these machines are in one location, owned by one company, so they can be more easily be taken out. So here we talk about full scale, Byzantine tolerant, fault tolerant protocol, which is a bit a different ball game, I would say. You can also compare it with Web 2 applications, but again, these are basically, very centralized and not as decentralized as what we aim for. And then there's other blockchains, famously, which maybe are as decentralized. For instance, Ethereum comes to mind, or Bitcoin, but they don't have the performance really right now. But of course, they will also improve, right? The most
Yes.
competitive, like what are I think really the competition comes for us in the future, probably from those, more centralized slash Web 2 protocols, which allow the same kind of smart contracts.
Yeah.
Not sure whether that's a good answer, but you can ask later again if you were not happy with this.
Yes, we can move on then save it to the end, I think. Thank you.
Good. Let's look at rotor first, okay? Oops, I have to always move my mouse again because I have too many screens today. So, sorry for the animation, kind of got carried away there. So rotor is the data dissemination protocol. Let's try to look at how this works. So what we do is over time, as seen in this picture, we produce blocks, okay? So blocks are basically the entity on which we have consensus. So the transactions go into blocks, and then every block we make a consensus decision that the transaction in this block should be accepted. They are, they are finalized essentially. Now let's look a little bit more detail. So we have here two blocks only, and on the right hand, you see that even the blocks are not the smallest entity we have, but we have slices. So basically this is used for pipelining. So when you build a block, then you just send out data constantly as a leader. If you produce such a block, you send out the data, one constantly, and you put them in little slices, okay? That's just little parts of, like when you cut a block of bread, for instance, or cheese, then you get slices. And we have shreds, and they are a coding thing. So each slice is just a bunch of shreds. And here I've shown the last slice just be a bunch of shreds. They are used for coding, and I explain it on the next slide. So when you're a leader, you basically send out these slices in forms of shreds, like this. We not only have the actual data here, but we have a bit of an overhead, okay? We have actually twice as many shreds as we need to send the data out. Let's look at this. So I'm currently the leader, let's say, and I have my current slice, and I just package the data in the slice into these shreds, and I send each shred to the relays. I have twice as many shreds as I need to recover the data from. This is, we use some coding here, some coding mechanisms, or maybe secret sharing, you could also call it. It's a very similar thing, where we basically make sure that if you as a user receive enough of these shreds, in our case, half of all the shreds that have been sent out, then you can reconstruct a slice. And this is true for every slice, then you can reconstruct a block. So when relays are just other nodes in the system, other so-called validators, the leader is also a validator, they're chosen pseudo-randomly. And when relays get this shred, then they just send it to everybody, okay? So this is what relays can do here in this little animation. So you send the shred to all the nodes. And now all the nodes receive some shreds. Maybe something is lost on the way. Maybe some are a bit slower than others. So as soon as you have half of these shreds, then you can basically reconstruct a slice and you can reconstruct a block as well. So this is a lot of work. So sending out these shreds to everybody, but we're gonna pay people who do that, okay? And we actually looked a little bit into this, and maybe that's the next slide, and I'll go over this very quickly. But we looked a little bit, how much more should we send out that we actually need? You know, we could say we have maybe 32 shreds per slice in reality, and we send out 64 or 80 or 96. And the more you send out, right, the easier it is to reconstruct in some sense. And also the more are the relays actually on the path from the leader to the receiver. So if I go back to this slide, so if you have the current leader, sends out to some relay. Now in the worst case, in some sense, the relay is on the other side of the earth, right? And then the relay has to send back to somebody who's actually very close to the leader. But in the best case, the relay sits somewhere either close to the leader or close to the receiver or somewhere in the middle of the two. So you don't have large detours. And if you do this right, as shown on this slide. So if you actually over-provisioned a lot, let's say by a factor of 10, then basically, you know, you almost have direct communication between leader and whoever receives the shred on the left side here. But we don't want to over-provision so much. For us, you know, 100 or so milliseconds is fine. So this is just the data dissemination. This is just to make sure that the blocks get to the nodes in the system. Now let's go for the other part. The voter part is a bit more interesting and maybe also maybe a bit more complicated. So this is how it works. So this is already how Solana works today. So we have these blocks which are produced. The picture looks a little bit different than before. Before everything was blue, now I have colors. What this means is just that we always have 4 blocks produced by the same node, by the same computer, and then hands over to the next computer, right? So here we have 4 blocks by one guy, and then the next guy starts with the 4 blocks and so on. And there's a little bit of a delay when you hand over between one leader and the next leader. Now, we want something, so before this used proof of history, but this is not a very good idea in my opinion. We have something better now. And we just use timeouts, okay? So how this works is, let's say the current leader B produces its blocks, so the red blocks or reddish blocks in my slide here. And what all the other nodes are doing, or what all the validators are doing, are basically, they're waiting for those blocks to arrive at them through rotor. And they have some sort of a timeout, okay? So the timeout starts, let's say, with the last, in the simplest case, with the last leader, okay? When the last leader sends out the last block, then we give time for the new leader to produce their blocks, okay? And actually, we don't not only have one timeout, but we have a timeout for every of these blocks. So even if B1, the first block of the new leader, if it comes late in some sense, then we would say this leader is not good. So what everybody now does, so we have maybe 1,000 nodes in the system, 1,000 computers which all share this work. These machines now just vote, was it in time or was it not in time? So you basically just have an upvote and a downvote, like in the picture. And you just check, is the block correct and was it in time? Let's assume it was an upvote. And again, what you do is you send this just to everybody else, okay, to the 1,000 other nodes which are in the system. So you send this upvote to everybody else, and you again get a little bit of money for this, okay? So this is work what we want to do is all the work essentially should be paid for, right? So whenever you do something for this blockchain, then you get a little bit of money. Now, okay, let's look at this case a bit more in more detail. So far I've seen these blocks. Let's say I take the position of this referee here, of this one validator, and I say, for instance, this block was good for me. Now I send this to all the other validators, but at the same time, all the other validators also send their vote to me. Okay, so that's it's some sort of an all-to-all relation. I send the votes out to everybody, and everybody also sends their votes to everybody, so also including me. So what we see here is basically I receive these votes now from the other guys, okay? And they have different stakes. So if somebody has a bit more money in the system, their vote counts a bit more than if somebody has less money in the system, basically linearly as much. And if 80% of the stake thinks that this block was in time and it was good, then we immediately finalize the block. Okay, so this is in some sense super fast, right? No other protocol works that fast. Usually they have multiple rounds of doing things. So we just have immediately a finalization. We can make a certificate with these votes. We just put those votes into something which is called a BLS certificate. That's just, you know, a fancy word for basically saying I have a cryptographic way to prove to you that so many people have voted yes, that 80% people have voted yes. There's a question online I see, and I think I just answered it right away. So the question is whether these timeouts are local or global, and they're completely local. So everybody does this for themselves. So if I go back to the previous slide quickly, so when I say I have this timeout, I really start a local timer with my system timer in my machine and say, you know, at that point in time, I want to have this block, right? If it's not there by this point in time, then I will gonna vote no. But this is not synchronized through the whole world, right? That would be very difficult, right? So everybody does this by themselves. I mean, they start at roughly the same time because they start essentially when they have seen the last thing, right, from the last leader. And if the last leader didn't cooperate, you have to go maybe back even a little bit more. But they start at roughly the same time, but it's never quite the same time because it's a worldwide system, right? You might see a 4 a little bit earlier from me, so you start the time a little bit earlier from me. Yeah. So we have this and we have this certificate. Now this certificate we can again send out to everybody. This is just to inform everybody that this block is final. And I really mean final here, right? There's no going back essentially, right? It's not that we can now say, oh no, this transaction, this block was not there. It will always be in the blockchain at this point already. Now, on the other extreme of the axis, we have a lot of downvotes, right? It could be that most people felt the block was either not okay or too late. And in this case, if we have 60% downvotes, then we immediately say we're going to skip this block. Okay, this leader did not behave, so we're going to skip it. So that's the idea here. Again, we make a certificate with that, so we can prove to anybody else that this is actually a skipped block. And we can send this out again. So same thing as on the right, basically. You see, it's a bit asymmetric, weirdly enough. And of course, there could be a case where we have, let's say, 50% upvotes and 50% downvotes, or maybe we don't even get all those votes because somebody is very slow, or things like that can happen. So for all the mixed situations in the middle, for everything which is not either on the extreme left or on the extreme right on my slide, we kind of have a mixed situation. And in this situation, we do one more round of voting, okay? So we can still finalize the block, we can still skip the block. It could go either way, essentially. A very typical case would be if we have 60% upvotes in this first round. This is not enough to finalize the block yet, but we can do one more round of voting with again 60%, and that would finalize it. We need this because I said at the beginning, we could have up to 40% bad guys in the system. So the 60%, you know, good guys essentially can make progress, right? Even if you have a very bad case of many bad people in the system. So, but there's other cases like this in this case. Now I could go into the details, and actually this slide basically describes the whole protocol, how you actually do this voter and what you do in what case. And we have basically 5 of these certificates and different types of votes and whatnot. We have something called fallback votes. This basically is used for if you don't have a majority for something, you could say, well, I don't see that this vote is going to get in, so maybe it would be okay if it's also skipped or something like that. Basically, these are the fallback votes where you would say either outcome would be fine with you. I will not go through the slide. Of course, that's something you can read for yourself, or you can ask questions as well. We've written it down. So this is, we wrote down a white paper quite in detail, I would say, quite academic, I would say, compared to what you usually get in the crypto world. And just to show how it works, and we even updated it recently with a few more, ideas. But let me show you how this works now. So this is from a simulation only. Okay, so we simulated Alpenglow in the early days, and what we can see here is a so-called histogram of latency. So you have here on the x-axis, basically, you have all the stake of Solana. Okay, 100% of the stake of Solana to the right, and let's assume the current leader who actually sends out the block is in New York. Okay. This is not very favorable for us, but let's just assume that this is the case. And now you can see here, what you see here is sort of this is the 200 millisecond bar here, and this is kind of the network latency. Okay, so this is how long it takes to send a bit from New York to other places who have stake in the world for Solana. Okay, you can see at the very left here, just behind the statue is basically zero network latency. These are the other nodes or the other stake which sits on the east coast of the US, right? And then maybe we have some other American nodes which are relatively close in terms of latency, so they see this very early. Then we have here a bunch of Euro nodes. So Solana, not unlike Ethereum, quite a bit of stake actually sits in Europe. This doesn't mean that this is owned by European people, but it just means that they operate machines out of, let's say, Europe. Okay, so that's basically what you see here. So this plateau is basically European nodes, which all have about the same distance from New York. And then we have the rest of the world towards the right? And there are some people which are really far away from New York. And now with Router, so with this data dissemination protocol I explained at the beginning, you see when actually these nodes receive enough of these shreds to make the slice and then the block, okay, to reconstruct slice and block. And you see it's a little bit more than the green curve, but not much more. So we cannot, the green curve is like a lower bound. We cannot get lower than that. And we have a bit of overhead, okay, but not much. And then after Rotor, we have voting. And first we see 60% of the votes. And this is the red curve, essentially. Again, there's a bit of overhead for that. And then we have finality at the end. And now, this is something I didn't say so far, but finality can happen in multiple ways, okay? So the simplest way, which I actually did explain, is that you see 80% of the votes. So you see 60% of the votes first. At that point, actually, you would send another message to everybody in case, this is the finalization. But you also keep collecting votes for this block. And if you reach 80%, then you already know, as I said before, that the block is final. Or it could be that you have this 60%, you send out to others that you think the block should be final at this point because you have 60% of the votes. And now it needs a second round of voting, essentially. Everybody does this who has reached this 60%. And at some point, you again reach 60% for this second round of voting. And that way, you can also get finality. Or a third way, actually, is that somebody just sends you a finality certificate, right? That's all possible. And basically, the blue curve shows the minimum of these three things, right, in our simulation at least. So, it's below 200 milliseconds. Before I claimed 150 milliseconds. And that's also true because New York is just not the center of the universe for Solana. It would be, if you have a European node doing this, then it's actually much faster. Here we have such a case, so maybe I've seen this. This was a little GIF which was on the web. Somebody kind of showed how Rotor would work in real life, right? So all the green dots basically mean some stake. And there's more machines, of course, in the world, but these are maybe the most important ones. And you see here a leader in Europe which sends something out, and then you see the others receiving the data through rotor. And I should say this is, 0.1x of the speed, right? This is like 10 times slower than in reality, just that we see something. And actually, people started implementing Alpenglow. We started doing this very early, but now Anza basically implements the real deal of Alpenglow. And there we even managed to get about 120 milliseconds from slot end to finality. So it's even faster than what we originally anticipated. This is with about a third of the stake sitting in the US or North America, a third of the stake sitting in Europe, and a third of the stake sitting in Asia. This 120 milliseconds, but it's still, just a 50 node network, so it might be a bit slower in practice or a bit faster if more nodes sit in Europe. Good. Let me mention some main open problems, and that basically will be the second part of my talk, right? So this is basically how the protocol works, all the main ingredients, the things we work on several things right now. One thing is what we call migration or switching, which we need a way to go from the current protocol to the Alpenglow, to the new protocol, right? It's a big change for Solana. I didn't explain how the current protocol works, but it's quite different. And we have to change that. And we don't want to, turn the whole thing off and then, upload the new software and then start the whole thing again. We want to basically change that while it's running, okay? So that's basically no outage. We just change the engine while we're driving. So that's, of course, very difficult, I would say, right? It's one of the most difficult things you can do as I would say, a software engineer or distributed systems person. And then the other thing which is important for us are incentives. How can we make sure that, that playing along this protocol makes sense, that people are motivated and that don't change things in order to make more money or stuff like that. But maybe it would be a good time to answer questions, and I think there are some.
Yeah, there's one.
Yeah. How relevant will the old complicated protocol be comparing? How relevant? I mean, if the new protocol is running, we never look back, in my opinion, right? So we don't. This is really replacing the old protocol. It's not something you put on top of the old protocol or something like that. This is replacing everything that we have. This is replacing this proof of history. This is replacing this, gossip eventually, and so on. So it will not be there anymore, but for the migration, when we go from the old to the new protocol, right, you never know what happens, right? So at that point, it might be good to be able to go back if something bad would happen or something. At least when we will test this protocol, we try to, of course, make this switch between the old and the new protocol many times to make sure that it works in all sorts of versions of failures that we could see.
May I also ask a question?
Mhm.
Can you scroll back to the one with cumulative graph? Though, yeah.
Which one?
Yes.
This one?
So if you can print it out all the color. So my question was more like each of those color. I think there, because this, I assume is simulation, right? There are some assumption we're making. For example, the network one, I think we're safe because they're pretty much AWS and so on. The router one, I think is also safe. Is a matter of how complex the thing you design. And I think the red one and potentially the blue one, especially the red one, you think it's going to be a function of how like what's their capacity of doing their job? Like are those nodes very like high performance? Like what's their
Yeah.
constraint? And second thing will be, as you mentioned, is their incentive, right? Like they may do something intentionally to screw things up. And the third thing is like how complicated the protocol itself is. It seems to me like it's a function of all three. So like I'm just curious, would something change the how big the red bound is, especially in some jittering time or some outrage?
Yes. So this is in some sense showing, first of all, this is showing in some sense the best case, right? So this is assuming that everybody sees the block in time, right? Everybody votes yes, essentially. And it's assuming that the current stake distribution that we basically see in the Solana network. When I say current, it's a few months back now, but it doesn't change that much, right? So it assumes many of these little things. That's why I had this slide at the very beginning with the apples to apples comparison, right? So depending on how this looks like for the competition, for instance, right, then it's always a bit unfair, right? So it would be good to, if everybody would say, this is exactly how we distribute our stake in the world, and then we can maybe make a fair comparison. So this makes all the positive assumptions. The protocol here, it only shows the good path. It only shows if everybody likes everything. And so there are many assumptions in this picture in some sense. I mean, the next picture which I showed, I didn't show it actually, but like on Twitter or on X, I should say, you can find newer data in some sense, not from our simulation, but from the actual 50-node network as it is tested right now. So this exists. Some people are publishing, some pics, some measurements there. But even there, we didn't implement all of the critical, all of the cases where something can fail yet. I mean, the paper studied all these cases, but the implementation is not yet there. So the implementation currently is just, the good case implementation, which we have already done. And yeah, so one has to take this a bit with a grain of salt. I would say, the order of magnitude is correct no matter what here. It will be much less than a second for finality. I mean, this part is, I know it's true, but how much exactly it will be in the end depends on so many things that yeah, that I wouldn't dare to tell you it's going to be like this or that. Yeah.
Thank you. I think there is another question in the chat.
Yes, so the question is about essentially the smart contracts or the programs, how they're called in Solana. Will they still work? And so this part we don't touch at all. So the code or whatever you have running still works the very same way, right? So the execution part of actually running code on this machine still is the same, and we need that in some sense as well, right? So if we make this migration from the old system to the new system, we could not change the code at the same time, right? Then all these things would break. And so, but this is exactly not only compatible, but it's exactly the same thing that we have right now. So this continues to work as intended. When you think of a blockchain, right, it usually has these two parts. It has the consensus part, which says, which transactions are now done, and it has an execution part which says what are the programs actually doing to your memory and who owns how much money. How are the votes tallied? So the votes are really sent directly between all the nodes. So we have about, let's say, 1,000 nodes in Solana currently. Try to keep that roughly. And we have about 1,000 validators. Some of them have up to maybe 3% of all the stake, okay? And some of them have maybe less stake. 3% of the stake is a percent in Solana is always like $1 billion or something roughly, okay? So they have $3 billion of stake that they control, and others have much, much less stake. But they will send the votes directly to each other, right? So when you send something out, we don't have a gossip network like other blockchains. We have so far, but we will not have in the future. We just send directly to the others, okay? And this sounds maybe like an overhead, but it's very fast, right? So these packets, the votes, for instance, are very, very small. And you can send, 1,000 small packets in, a few milliseconds. There's nothing that holds us back in some sense. So, and so you just receive that, and you have a receiver process basically, which just gets these votes from the others in, and this just checks have I received enough votes to go to the next step in the protocol, right?
I
And
think
typically, yeah.
there are one more question, and there's also Hannah want to ask a question. Basically directly say the question also. Like maybe you can answer the question. The Itamar answer, like it's in the answer section. Like is there a reason that in this graph the green part flattened out My guess is there are too many European nodes, but
Oh yeah, the flat part in the middle is European nodes.
that's
And
and
also at the end it flattens out. I don't quite know why this is, but there's probably some nodes which have, quite a bit of stake. Maybe it's even 4% or something like this at the end, right? And they sit somewhere far away.
yeah.
But I don't know where it is.
And then I will unmute Hannah from NYU and she'll ask another question. Yeah, Hannah, I think you can speak now.
Okay. Yes, thank you. Thank you very much. So I wanted to just ask a follow-up question on voter about the tallying of the votes. So the voters do not need to send the same vote to the other nodes in the network, right? So they can be Byzantine and they can send upvote and downvote to different parts of the network. So how are you protecting against that? And yeah, I know you mentioned that you are protected only 20% of Byzantine nodes, but how is this happening?
Yeah, so that's a very good question. So of course, if you are bad, right, you could do that. You could basically lie. The idea is that the good protocol would not do that, right? Like a good node who wants to play by the rules would not do that, but others would do it. Now we could punish you for such behavior, right? So votes are signs. So if you vote yes for the same thing as you vote no, those two things together would be an immediate proof that you're a Byzantine person, and we could punish you for that.
So
Now,
who would be punishing?
who would be punishing? We don't know yet, because I just wanted to say this is not something we do at the very beginning. It's not something we actually expect to happen. But we will. I will talk about incentives in a second, and then maybe we can talk about this again. But it's something we have in mind, of course. If we see it coming or we have more time to improve the protocol, then we will actually do this. Solana somehow famously currently does not do this punishment. Okay, so if somebody does not really play by the rules, it's kind of like just the Solana community would give them a bad eye essentially. Okay, so that's sort of what they do right now. This is not, the good answer for the best possible blockchain in 2 years from now, but we take it one at a time. And I think at the beginning we will live a little bit with this problem that somebody could do this thing. But why would you do it? You wouldn't profit from it in some sense, right? It would be a shady thing to do, and you don't make more money if you do this thing, right? It just cause a bit confusion. But like we have some sense secret margins everywhere, right? So that's why we only have 20% plus 20% security. So if only 20% do that, actually the protocol still works perfectly fine, right? There's nothing bad can happen. If everybody would
Thanks.
do it, then of course that protocol would be in deep trouble, right? Then everybody, somebody just gets yes votes, another person just gets no votes. For that person, the block is skipped for sure, and for the other person, the block is in for sure. Then we would have problems. But in some sense, every blockchain has this a little bit. Yeah.
Thanks.
Yeah. Thanks. So another question. Timeouts and neglect. Yeah. True. Okay. So the communication. So I explained it as in the very simple case where everybody just always talks to everybody else. Okay. But you could use other things. And what I didn't mention in this talk is something called double zero. They are building, a new internet in some sense, a private internet. And this internet already exists, and they have a bit of functionality that the normal internet does not have. For instance, they have a functionality which is called multicast, where one node can just send a message to everybody, but without the overhead of actually having to send all the messages one after the other. And so we can use that as well. So in both voting and in rotor, I always had these little rainbows, basically, this golden, I don't know how to call it, fans at the bottom out. And so basically, instead of doing that, if you are part of that network, you could also just send to everybody by multicast, or you could do both just to be on the safe side, right? Then maybe the multicast would be a bit faster. it's no big overhead because you just send one more message, right? You send 1,000 and now 1,000 plus one. And whatever is faster is better. And we don't really want to adjust the timeouts, I think, at least not initially. We have some timeout, which is, safe for everybody. We don't want centralization, we want decentralization. And usually the timeouts should not fire, right? The timeouts only fire if something bad's going on. If the leader is just correct and makes a block and sends it around, then it should always be an upvote saying, yeah, I got the block. I hope I answered Andreas' question. Julia, the biggest reduction in latency. So yes, so that's a expert question in some sense. So hot stuff also has, there's this hot stuff 2 and hot stuff 1, and there's different versions of it. And I would say the most advanced versions, they also have one round of voting. So this is a concept which has been known actually since Leslie Lamport. So he already knew that this exists. What is new here, what we use for the first time, I would say, in a practical protocol, which has been introduced with this Banyan paper, is that we basically do the one round voting and the 2-round voting at the very same time. Okay, so they both start at the very same time, and whatever is faster wins, so to speak. So that's the new thing. So that can help you. In particular, if you think of a system where a lot of stake sits in the same place, let's say in Europe for practical reasons, let's say 70% even of the stake sits in Europe, then actually 2 rounds is faster than 1 round, weirdly enough, right? Because 2 rounds among the 70%, you send the block out in Europe, let's say, you immediately reach 70% of the stake. This stake sends the votes to everybody, but immediately you get 60% of the votes if you're sitting in Europe, and then you do a second round of voting again, everybody to everybody, the 70% to everybody, and then the 2 rounds of voting will be super fast, right? And the 1 round of voting, you need votes from outside Europe for that, and that could be actually slower. So what is new here is that this is actually, in some sense, faster than what has been known before because it combines those 2 things. And tag-based protocols, so that's even a bigger can of worms. So they also have some problems, I would say. For instance, when we talk about how many rounds they actually need, they would also argue that they only need essentially 2 rounds of voting, if I might simplify a little bit. But that's just for one of the nodes, and the others actually need a bit more rounds of voting. So they're all a bit slower, right? So even if they, on the same playing field, we are faster than these things. And I think we are, 1 round of voting, you can't get faster than that. So I think we are sort of like hitting the lower bound. Yeah, and then Kobe. Is there non-malicious reason for a voter to vote no? Yeah, there are non-malicious reasons to vote no. In particular, if you just be honest, right? So if the block comes too late, then you vote no on the block, even if it's just a millisecond too late. I think that would be the main reason probably why people will vote no. Now you might say, why would this ever happen? But it could be that somebody, if you use a bit more time to produce the block, maybe you can make a bit more money, and then so that's yeah, that could be a problem. So if the vote fails, I mean, if actually a majority, or like as I showed at the beginning, 60% of the votes are negative, then you would basically skip the block, right? So the next block would just be built on top of the previously accepted block somehow. So that's, we just skip it then. This is something which comes from the simplex protocol. Okay. But I'm not sure how much I should go on, but maybe I just show a few more slides and then we have more questions or so. Is that okay?
Sounds great.
So maybe this is an insight I had at some point, right? So, and this is sort of like similar to the discussion we're just having. So when we talk to the validators, they would of course tell us and tell everybody that they're not Byzantine, right? They follow the rules and that they by and large do. But if you kind of expose something as a game, okay, if you kind of tell them, oh, you could make a little bit more money by doing that, then they would absolutely do that as well, right? So in some sense, then they would become, selfish, but selfishness becomes Byzantine at some point, right? Or, it could harm the system. So we looked into incentives quite a bit, and this is just a slide which shows you what currently the incentives are and how we want to change them. So the red part is always the Alpenglow version, and the white part is just the current version. So currently, they also have some sort of voting system. They can have forks in the chain, and then they have to vote on which block they want to accept, like other blockchains as well. But now they have a bit of a punishment if you vote differently from everybody else, okay? So if you vote on the wrong thing, let's say you have a sort of a branch or a fork, and now you could vote on either this block or that block. And then if the majority votes for block A, but you vote for block B, then you get punished, okay? So what happened is that people would then delay their votes and they would first wait and see the other votes. This actually is quite a slow process because so far the votes go actually on chain. They're not just sent to the others. And so you would just see and wait on chain what happens. And this is already, 800 milliseconds later or something when you see that, the earliest time. And so you delay it. And then people, of course, everything will get slower. And this actually happened for Solana. And then they had to introduce something like timely vote credits, where you say, but you get more money if you vote earlier, okay? And this is also not so easy because somebody in Australia might have a disadvantage again, right? So it's always a bit of a trade-off for these things. So for us, this is all gone, right? So what we see is just, what you see is what you vote, right? You don't scheme, you don't need to scheme. If you see the block is in, you vote yes. If you see the block is not in, you vote no. You get the same reward no matter what, okay? So that's the idea. Makes it much simpler from a game theory point of view. And so far we have rewards for individual nodes, votes, because they go on chain, this is easily possible, right? Everybody sees those votes, and then basically you can just give a little bit of reward. Now we don't have these votes anymore. What we have instead is aggregates. So we have vote aggregates. So since votes are just sent peer-to-peer, from time to time, for every block, basically, somebody collects all the votes they have seen, and then it puts again such a BLS certificate on chain, right? Doesn't have to be a certificate, just all the votes it has seen for yes and for no, puts this on chain, and then people get rewarded for this, right? So if they have their bit marked in this message on chain now, and it's a small message, everything fits into a single UDP message here, then you basically get your reward. For the one who has to put the block or this aggregate on chain, gets also part of the reward, right? Basically, half of it goes to the leader, half of it goes to the actual voters. And this sounds unfair because the voters have more work, but everybody's leader and voter, with about the same probabilities. So it doesn't matter that much. And since so far votes go on chain, and Solana is kind of famous that a lot of the traffic, maybe 20% or something like this of the traffic is actual votes so far. So this costs them a lot to just put those votes on chain. It costs you about one sols, about $220 of today's value, I think, to move that on chain. And so that costs you, per day about $220. So we don't want to, with Alpenglow, we don't want to change the economics too much. We want to keep them the same so that we kind of have the same system as before. We have the same validators with the same stake at the beginning at least, right? So that we don't, totally have a revolution of the system. So since this doesn't happen anymore, we just we have vote aggregates here, so we don't have this anymore really, but we want them to pay a little bit, right? So first, validators were very happy about this, that we said this goes away. But if this goes away, then basically everybody wants to be part of the system. And if everybody wants to be part of the system, then it just becomes maybe, a bit overcrowded. And maybe eventually we can allow that, but at the beginning we don't want to allow that. So we want to maybe have slightly, lower, just what we call a validator admission ticket. You just pay a little bit per day to be part of the system. Don't feel too sorry about these guys. They also make money from transactions and whatnot, right? And they have rewards. So this is sort of like how this is going to change. And maybe I'm going to jump a little bit ahead. So maybe I show this quickly. So with Alpenglow, just basically a repetition. I get a reward for my vote. It doesn't matter what I vote, right? I can just be truthful. I don't want to be punished. I will not be punished for voting the wrong way, right? Don't have to know what others vote. I don't have to speculate. I can vote as soon as I can, and I have to vote eventually. So I can also do it, when I can. There's no, from a Nash equilibrium point of view, there's no real reason to deviate from this. But of course, if you talk to validators, then they have ideas, okay? For instance, they would say, no, I just skip now all the time, okay? I just say no all the time. And true, they will get, the same money as if they actually truthful did it. I would say there's no real reason to do it because it's the same work, right? But they fear that this is a problem, okay? So you gain nothing, get the same reward. The action is visible also, so the aggregates are on chain. So we would see that you always vote no, okay? And you could probably, social pressure would say, we can talk to you. But this is something that I discussed a little bit with them, and just to show you a little bit, it's not all so easy, right? So whereas as a scientist, I always felt that the Nash equilibrium decision, the Nash equilibrium definition makes sense in the sense that if you cannot make more money, then you would not deviate. They think they might still deviate even if they don't make more money, and that of course would be a problem. So, and let me skip this a little bit. So there is, this old solution where you have these timely vote credits, but I think this sums it up quite nicely, right? So for Alpenglow, we just assume this on the top, right? We assume that this is the natural thing to do. On the bottom, it's, you have to speculate with the votes. Now the system gets very slow. Then you need a countermeasure. This is why they had these timely vote credits. Now the Australian validator is somewhat in trouble because it doesn't get the same credits. So you would say, well, I'm closing down my machine in Australia and move it to Europe. But then eventually everybody will be in Europe, right? So then you have basically centralization. And then you might say, well, maybe it's even better to everybody was in Amsterdam or something. And in the end, really, you have a centralized system. And then we cannot argue anymore that we have a worldwide decentralized system. So this is, in some sense, a tricky business. Let me skip over this. This was sort of a joke when I talked to the validators. I told them I have a solution and they all applauded, and then I showed them that this solution doesn't work. So, this sort of game theory thing is really tricky to understand. So let me come to a conclusion. So for Alpenglow, thanks to ChatGPT for making this picture for me. It's not real. But what we definitely want to solve, okay, and what we have solved with Alpenglow is that if you deviate from the protocol, if you change the code, you cannot make more profit, okay? So this would be catastrophic. If you can make money by changing the protocol, then of course people would absolutely do it, is my opinion, okay? So we don't have this, okay? So we make sure that we are in some sense incentive compatible, that you make the most money if you just keep the protocol. However, you could argue that you want to deviate for something else, maybe not completely, Byzantine. That's one way to deviate to be completely Byzantine, but maybe that's not happening so much actually. But you could say I'm deviating because I can save a bit of work or something. I get the same profit, but I'll save a bit of work, right? That makes sense. That would also not be great. It's not catastrophic maybe, but it's not great. But this is actually much more difficult to solve, okay? So that's sort of like my message here. So if we had a blockchain protocol which is fully incentive compatible, okay, which means that whatever work, for instance, you have to do, you do it because it's the right thing to do. You make a bit money by doing it. It's actually profitable. That would be the best thing. I would argue that no blockchain today has this, okay? So every blockchain has some parts in, for instance, gossip-based blockchains, you get the message, you have to send it forward to other people. And it's not, you don't have to do it, right? Just don't do it. You save a bit of work. You don't get anything for it. So everybody basically has an incentive if they want to deviate for X to not do it. So to solve this is not so easy. I mean, we're working on it and we have new ideas, but we're still working on it. Let's put it this way. Good. So with this, I really want to finish. And I take questions after that. So I just presented to you Alpenglow, Solana's new consensus protocol. It has these rotor and voter parts, just some pictures to remind you, and we showed a little bit how fast it is, and we have these incentives, which are an interesting question.
Thank you so much, Roger. I think you already answered this question in the chat because that's what you just talked about Australian validators
Yes.
being moved to Europe.
Yeah. So we want to make sure that they don't earn less, right? We want to make sure that everybody earns the same, no matter where they are on the world.
Yep.
And so that's important to us because otherwise we have centralization.
Yeah, if there is no more question, and if you have time, please see if there's more question. But like, I have one more question. So imagine nowadays if I'm bring in some validator, but they don't have the same level of machine compared to existing validators. How much this will impact all those performance of this new protocols?
Yeah, so you say if there's a machine which has, so Solana is famous for asking the validators to have good machines, right? So you
Yeah.
say if somebody has a bad machine. True. So first of all, this protocol is easier on your machine than the previous protocol. Okay, so that's maybe also important to tell you. So we bring down bandwidth quite a bit for the same throughput. Essentially, we have less overhead, and also the computational overhead will actually go down a little bit. So, but it could still happen that somebody has a very bad machine, right? And this, in some sense, is a problem, mostly also for that person, because this would mean, for instance, that for execution, this node would lag more and more, right? So if you are slower than the other machines and the other machines advance at some tempo, and you're just slower than what they advance with, then you're basically in trouble, right? Then you cannot, then you're not useful anymore at some point because you don't even know what the state of the system is anymore at some point. So you need to be able to keep up with the others. And as long as you're able to keep up with the others, then you're also able to do the thing they have to do, essentially, I would say. So
Makes
it's
sense.
a bit of a problem, but I would say it's more an academic problem than probably a realistic practical problem.
Yeah, the intuition I was thinking about is like from the perspective of a very slow node. When they vote, because they're locally voting, then their state of world may be very different from other hyper-fervent nodes' state of world, and then either they're just kicked out from the mechanism or they bring some trouble to the mechanism.
Yeah, yeah. No, of course it's important. If you have the only potato machine in the whole network, then of course then it could be that we just lose touch, and then you probably would not be a validator anymore, just give up or buy new hardware or something. But if, of course, if many nodes have this problem, right? If 20% or something have this problem, then
Yeah.
then that would be in some sense, like they are crashed essentially, and then at some point maybe the protocol would not make progress so fast, but we are not yet at the boundary where we could say, we just always 2 times the speed next year or something. That's not happening so quickly, I guess.
Andrea has a problem on.
Yeah.
Yeah.
So the question is, can a leader basically send 2 blocks for the same slot, right? Yes. So with Rotor, this is something we discussed in the paper at length, actually, this equivocation. With Rotor, this is possible, I would say, that you do that. You just send it, but the problem is then, like you send half the shreds to one, different, let's say block A, you send to half the relays, and block B, you send to the other half the relays. But then basically, if you don't control all these relays, and you wouldn't do that because that would be 100% Byzantine, Then, of course, most nodes would see that you send two different blocks for the same slot. Now, what would they vote, right? So it could be that first they would still, vote yes. And if you actually send block A a little bit earlier than block B, then maybe most people will get block A earlier, and then they would vote yes for block A, and it could be that block A even gets in. Now, if we see block B later on also signed by you for the same slot, we again know that you're Byzantine, and we could potentially punish you for that. Whether we do it is a different question, but it's a clear punishable offense.
Maybe last
Yes.
question. This
Yeah,
should be an easy one.
leaders. So we have about 1,000 nodes, and the leaders are just chosen randomly or pseudo randomly according to their stake, right? So the 3% stake node, for instance, would be chosen for about 3% of the slots, essentially. And it would also vote for everything, but its voting power would also be 3%. So everything is basically always dependent on your stake.
Yep, it's the proposer. Thank you so much, Roger, and thank you for taking the time. And we have enjoyed it a lot. And if there's no question, I think it's a time to end.
Yeah, or send me a message, okay, on either X or email or whatever. I'm sure you find me because my last name is quite unique.
Okay. Okay. I
Okay.
will.
Thanks everybody for coming.
Thank you so much.